the concept of set theory. A set is a clearly defined collection of things, objects, or numbers. Now we have finite and infinite sets. A finite set is a set, like if we have a set A containing the elements, we normally denote the set by capital letter, then the elements by small letters. Then if we can count the number of elements in the sets, we call it finite sets. Then if we cannot count the number of elements in the set, for instance, if we have a set B containing the elements 1, 2, 3, 4, 5, if this set contains the natural numbers, we say that this set, because the natural numbers are infinite, we say that this set is an infinite set. So we have another one, subsets and supersets. When we say that a set is a subset of another set, look at what we mean. If we have a set A containing the elements A, B, C, and then another set B containing the elements A, B, C, D, E. Now we find out that in this one, everything here is contained here. So we say that A, look at the denotation, that A is a proper subset of B because A is contained in B. Then supersets, that's the opposite. If A is a subset of B, then B is superset of A. Then another one, we have equality of sets and equivalent sets and equivalent sets. Here, what equality of sets means is that a set, when a set A containing the elements A, B, C, then we have another set B, no matter the order. For instance, we say B, A, C. Now we found out that this set is equal because all the elements, this is this, and this is this, all the elements in A are contained in B, and all the elements in B are contained in A. In this case, we say that the two sets are equal. Then equivalent sets, we may have two sets A, B, and C, then B to be 1, 2, and 3. Now they have the same number of elements, but their elements are not the same. In this case, we say that they are equivalent sets. Now another one here, we have the universal sets. We have the universal sets. The universal sets. This is a set that contains all the elements in consideration. Like here, using this example, A, B, C, then B, we have 1, 2, 3. Then their union, which is denoted as A union B, is a set that contains all the elements in consideration. And look at it, 1, 2, 3, A, B, C. This is the union of these two sets. Now, we also have the singleton. We have the singleton. We have the singleton, or we say the unit set. Now this is a set that contains only one element. Only one element. When a set contains only one element, we call it a singleton. Now we will also note that this is also a singleton because the only element it contains is 0. Again, we have the empty set. We have the empty set. The empty set is a set that contains no elements and is denoted as is either you see this or you see this symbol. This is the symbol for an empty set. Also, we have the complement of a set. The complement of a set. In the complement of a set, this is the elements that are not contained in a set. If you have 5, 6, 7, 8, so here set A, then we have another set B, 1, 2, 3. Here now, the complement. So here we have the complement of a set. Assuming we have a set A, 5, 6, 7, 8, and B, 1, 2, 3. The complement of A are those elements that are not in A, and that is 1, 2, 3. And likewise the complement of B, those elements that are not in B, 5, 6. Now if we have a complement of a set and we have assuming a set 5, 6, 7, 8, then another set 1, 2, 3. The complement of A will be 1, 2, 3 because 1, 2, 3 is not in A, and the complement of B will be 5, 6, 7, 8 because 5, 6, 7, 8 are not in B. Now another one is the cardinality of a set. The cardinality of a set. Now in the cardinality of a set, we are looking at the number of elements in a set. Now if we take this example here, the number of elements, that's the cardinality of A, is what? The cardinality of A is 4. Then the cardinality of B, here we have it to be 3. So we also have disjoint sets. We have disjoint sets. Now disjoint sets are two sets that have nothing in common. For instance, these two sets we have here, 5, 6, 7, 8 and 1, 2, 3. You notice that they have nothing in common. In that case, we say that they are disjoint sets. They have nothing in common, and they intersect, and they have nothing in common. Then another one we'll discuss here will be intersects. The intersects of sets. Now the intersects of sets are the things that a set have in common. If we have a set A, B, C, and another set A, 1, 2. Now the intersects of these two sets, which is A intersect B, will give us what? Will give us A, because they have A in common. And if we come to these disjoint sets, the intersect, since they have nothing in common, the intersect of a disjoint set is empty. That is a null set. The null set that we discussed here, the empty set. We have another one we call the power sets. Now the power sets are the number of elements you can get in a set. this set A, B, C, then the number of elements we can get in this set, number of subsets, not just element, the number of subsets. Because if you say the number of elements you can get in this set, you'll be talking about the cardinality of the set. So the number of subsets that you can get in this set are, we have first of all the null set. Again, we have A, we have B, we have C. Now another one, we have AC, A comma C. Another one, we have AB. Then another one, we have B comma C. Now how many subsets do we get here? 1, 2, 3, 4, 5, 6, 7. Another one will be A, B, C, and those are the subsets we have. Those are the subsets we have here. Now, what else I want to show you here is, for instance, if you have a trumpet, the number of keys you can get in a trumpet, like if you press this one, press this one, press this one, the number of keys, number of sounds a trumpet can make is 8. Now, look at the concept that was applied. The concept that was applied was the power set of these three things. The formula is 2n, and then if this n now is 3, that's the cardinality of the set. We have 2 raised to power 3, and that is 8. And if you count it, do, re, mi, fa, sol, la, ti, do, that is 8. That's where the concept is applied. Now again we have the Venn diagram. Here we have the Venn diagram. Now the Venn diagram is a diagram that is used to solve real life cases. Here, this is the number of persons. This side is only this place. Then we also put union here. Then this union is equal to this side plus this side plus this side. Watch out for the next video for the examples on Venn diagram. Thank you.